Have you ever stopped to think about the hidden math that gets, planes and ships and even our GPS satellites exactly where they need to go? Well, today, we're going to pull back the curtain and dive into the world of vectors to see how it all works.
So, let's kick things off with a classic puzzle. Imagine a pilot is pointing their plane due east, engines going full blast. But at the exact same time, there's this strong wind blowing directly south. So where does the plane really go? Does it go east? Does it go south? Or somewhere else entirely?
For anyone in that cockpit, figuring this out is absolutely critical. See, it's not just about the plane's own power. It's also about the force of the wind pushing on it. Nailing that calculation is the difference between a perfect landing and, well, being miles off course. No room for error.
Okay, so let's break this down. This is what we're calling the pilot's dilemma, and it's all about understanding these competing forces.
And really, this isn't just a pilot's problem. Anytime you're trying to move in one direction while some other force, like the wind or a powerful ocean current, is pushing you in another, you are dealing with this exact same puzzle.
So how in the world do we solve this? Well, we need a special kind of mathematical tool. It's called a vector, and it's basically the language of magnitude and direction.
All a vector is, really, is a way to describe something that has both a size and a direction. It's not just about how fast, it's about how fast and which way. You need both pieces of that information for it to make sense. Here's the easiest way to get it. If I just told you to walk 50 paces, that's not a vector. Sure, you've got the size, the magnitude, but you have no idea where to go. But if I say walk 50 paces toward that big tree, bam! Now you have both magnitude and direction. That's a vector.
And what's so powerful about vectors is how flexible they are. It doesn't matter if you're looking at a flat, two-dimensional map or moving around in the real three-dimensional world. The same exact math principles work perfectly.
All right, now for the cool part. Let's see how we can actually combine these forces, how we can add them together to find out where our pilot is truly going.
Visually, adding vectors is surprisingly simple. First, you draw an arrow for the plane, its speed and its heading. Then, right from the tip of that first arrow, you draw a second arrow for the wind. The final step? Just connect the start of the first arrow to the end of the second one. That new line? That's your answer.
And this third arrow has a name. It's called the resultant. Its length tells you the plane's actual speed over the ground, what they call its ground velocity, and the direction it's pointing is the plane's true path through the sky.
Okay, enough with the theory. Let's plug in some real numbers and actually solve the puzzle we started with. So here's our scenario. We've got a plane, and it's flying at a pretty speedy 550 kilometers per hour. But at the same time, it's getting hit by a 60 kilometer per hour crosswind. The question is, what's its actual speed and direction now?
Well, when we do the vector math, we get a super clear answer. The plane's true speed is actually 505.5 kilometers per hour, and its course has shifted. Just like that, the pilot knows exactly where the plane is really headed.
And this doesn't just work for planes. The exact same idea applies to, say, a ship that's pushing forward at 30 knots while being shoved sideways by a 14-knot current. It's the same problem, just on the water.
And yep, the math is just as reliable at sea. We add the ship's vector to the current's vector, and that resultant gives us the true course and speed. It is a beautifully consistent system.
So here's the real mind-bending takeaway from all this. Pilots and ship captains, they don't actually point their vehicles right at their destination. Instead, they aim where the combination of vectors, their engine plus the wind or current, is going to take them. They fly the equation, not the landmark.
But believe it or not, just adding two forces together like this, that's barely scratching the surface of what vectors can do.
There are other operations that are just as powerful. Something called the dot product can tell you how much two forces are working with each other, or against each other. And the cross product is even wilder. It can reveal a totally new force that pops up in a third dimension when two others interact. That's absolutely crucial for things like physics and engineering.
And the truth is, the applications of vectors are just everywhere. The physics engine in your favorite video game, that's all vectors. Your phone's GPS finding your location, vectors. 3D computer graphics, weather forecasting, even designing a bridge, they all depend on this fundamental tool.
Which kind of leaves us with a final thought to chew on. Right now, we use vectors to understand the forces we can see and feel all around us, like wind and water. But what about the invisible forces? What unseen forces, maybe in physics or finance or even biology, are just waiting to be discovered and understood, all through the simple, powerful language of a line with a length and a direction?